Looking a little bit more at max and mins, inflection points, intervals of increase, decrease, and concavity. Just to review, max and mins can happen where your first derivative equals 0 or does not exist. Inflection points happen where your second derivative is 0 or does not exist. Intervals of increase happen where your first derivative is greater than 0, and decrease is where your first derivative is less than 0. For concavity, the function will be concave up if the second derivative is greater than 0, and concave down if the second derivative is less than 0. Example 1 is the function f of x equals 5x to the 4 plus 6x to the 9 minus 5 increasing or decreasing when x is equal to 4. We could go through all of our steps of finding our critical points and finding our intervals of increase and decrease, and then looking for which interval x equals 4 falls into, but that's a lot more work than we actually need to do. We don't care what all of our intervals of increase and decrease are, we only care what happens at one point. So what we can do instead is just find the value of the first derivative at x equals 4. If it's positive, it means the function is increasing at that point, and if it's negative, it means the function is decreasing at that point. If you're asked to show your work, you're going to show finding the derivative, and in this case it's a nice power function, so hopefully it's not that bad to find this derivative. And then we want to know what happens at 4. So we're going to take 4 and we're going to sub it in. You're always going to show what you're calculating. Don't just write down a number without having proper notation to show what that number is. And we should get a really, really big number. The value of that number doesn't actually matter. What matters is that it is a positive value. So this is greater than 0, therefore the function is increasing. Example 2 is the function f of x equals 2x cubed minus 5 root x plus 3 concave up or concave down when x is equal to 2. In this case, we're talking about concavity, so we should be finding the value of our second derivative at x equals 2. If you're asked to show your work, you're going to have to find both derivatives by hand. If you're asked to use your calculator, you can use your calculator for the second step, but you still have to find the first derivative by hand. And before we do that, we're going to change how this function looks. We don't like roots, so we're going to rewrite that to be an exponent. Once we have that, we can find our first derivative. And if you're allowed to use your calculator at this point, you're going to write down what you're calculating. You're finding the second derivative at 2. You're going to use your calculator's derivative function and treat this first derivative as the function that you're putting in your calculator. And you should get 24.4 when you do that. If you're asked to show your work, you would have to find that second derivative by hand first. And then you can sub in the 2 and show what your answer is. Either way, we get 24.4. That is a positive number. So if you remember from our concavity, when our second derivative is positive, it means our function is concave up. So we're going to write down that it's positive, it's greater than 0, and then we're going to write down our conclusion. Concave up. Make sure you're writing out in words whether it's concave up or concave down. Example 3, we're given a graph and we're asked to find some things on the graph. So the first one says to find the local maxima. So local means it is the highest point in a given interval. The first one that I see is A. We are assuming this is on a closed interval, so the graph doesn't continue past this. It actually stops at these endpoints. So A is a local maxima. The next point we get to that is the highest point in an interval is going to be F. And then it goes back down, it comes up again, so J is going to be a maximum. I think we're missing a point labeled in here. There's a minimum right here that is not labeled, and then K is going to be a maximum again. The second thing it wants us to find is the absolute minimums. Absolute means it has to be the lowest point on the entire graph. There's only going to be one of them. If we look at the graph, it looks like the lowest point is D, so that would be my absolute minimum. Intervals of concave up. Concave up means it looks like a parabola that's opening up, or it looks like the U in the word up. So we're looking for that shape in our graph. And if we look at the graph, when it starts, we look like we have a parabola that's opening up. At B, it looks like it's switching. So now it looks like it's a parabola that's opening down. So we don't want that part, but we want the interval A to B. Switching to open down here from C to D, again, it looks like a parabola that's opening up. So we're going to include that part. After D, it's still looking like a parabola that's opening up. I guess you could have listed that as C to E. You could have listed that all as one interval. From E to G, it looks like a parabola that's opening up. Here we're switching to a parabola that's opening down again until we get to I. So I'm going to list that one as one interval. And then we're flipping again to be a parabola that's opening down until we get to this point that I didn't label. Let's call that L. Well, there's probably a couple of inflection points in there that we're missing because it's kind of small in there. We'll say L goes down, and after that we'll say it goes up. There's probably a few inflection points between these where it's switching, but it's pretty close together there. Inflection points are everywhere where your concavity changes. So if we look at what we drew, our concavity is changing here. And then our concavity is changing at C. Concavity is changing at E, G, we're switching, I, we're switching, and we said L, even though that kind of looks like a minimum. It's not really an inflection point, but things are a little bit squishy in there. The next part, we're going to find all the places where the first derivative is greater than 0. So we need to think about what that means. First derivative is talking about increase and decrease. So if our first derivative is greater than 0, we're looking for all of the intervals of increase. So the graph starts by going down. It's going to change to increasing from D to F. So there's our first interval. And then we go down again. H to J is increasing. And then we're going to put this minimum in again. L to K is going to be increasing as well. Next part says find the places where the first derivative is equal to 0. So we have horizontal tangent lines. Those tend to happen at max and mins. So if you're having a question that says where's the derivative equal to 0, you're looking for all of the max and mins. We're not going to include the endpoints. Our derivative's not horizontal. They are max and mins because they are endpoints of the intervals on a closed interval, but they're not going to have horizontal tangent lines. So the first one, well, actually we probably have a horizontal tangent line here as well, even though it's not a max or min. Normally you're not going to see ones like that. Normally it'll just be your max and mins that you have to list off. So D, E, H, and then J, and L. Then we're asked to find all the places where the second derivative is greater than 0. So the second derivative is positive. Positive second derivative means we are looking for all of the intervals of concave up. And we did list these on the last slide, so maybe I will leave those. They're going to be the same as the last slide. Instead of listing all those out again. A few more questions. Sometimes you're asked to find points where two things are true. So we know something about the first derivative and the second derivative. First one, we're looking for a point or an interval where the first derivative is greater than 0. So first derivative means increase or decrease, and greater than 0 means we're increasing. And the second derivative equals 0, so that means an inflection point. So we are looking for an inflection point where the graph is increasing. So first of all, we have to be on an interval of increase and decrease, and then we have to be at a point where concavity changes. So here's one of them. We can list E. I is another one. It's an interval of increase, decrease, and our concavity is changing there. So there are a couple of points. The second part says find all the points where the first derivative is 0, so that means max or min. And the second derivative is, again, positive. Positive means concave up. So all the max and mins where the function is concave up. Well, here's one of them at D. H. And if I label this one again as L, it is concave up there, so L is going to be another one. If you'll notice, these are all minimums. Draw an arrow to a point where the first derivative is 0, so that means max or min. And the second derivative is negative. Negative is going to mean concave down. So we want first derivative 0, concave down. We could use this point, E. It is a max or min, it's concave down. We can use J. I think those are the only ones we've got. So you'll notice those ones are actually maximums. And if we know that we have a critical point, so we have a first derivative that's 0, if our second derivative is positive, the only way we can get a horizontal tangent line if we have a graph that's concave up is if we're at the bottom. So we have to have a minimum if our first derivative is 0 and our second derivative is positive. Same thing for if we have a critical point and a graph that is concave down. The only place on a concave down graph where we have a horizontal tangent line is going to be at the maximum. And that brings us to the second derivative test. The second derivative test says if you have a critical point, so you have to have a critical point, you have to have a point where the first derivative is 0 for this to work. So if you have a critical point and the second derivative is positive, we know positive means concave up, there's a local minimum at that point. If the second derivative is negative, we know negative means concave down, you're going to have a maximum at that point. And if the second derivative is equal to 0, the test fails. We don't know if there's a max or a min or neither. It could be any of those. You would have to go back and use the first derivative test to check and see what happens at that point. Example 4, find the max and min values of y equals 2x cubed minus 9x squared plus 12x minus 3. We're looking for max min, so the first thing we need to do is find our critical points. We still need to use our first derivative to find all those critical values where a max or min could possibly happen. Which means we're going to find our derivative. And critical points happen where either that derivative is 0 or where it doesn't exist. It's not a fraction, so we don't have to worry about looking for where that derivative does not exist. We're only going to have critical points by taking that derivative and setting it equal to 0. It's a quadratic function. You could factor this, or you will always be allowed to use your calculator's equation mode to solve cubic and quadratic functions. So however you choose to solve that, you should get 1 and 2. Now we could make our number line, marking those points on our number line and testing a test point in each interval to figure out what the sign is, to know if our function is changing from increasing to decreasing or decreasing to increasing at those points. That will work. That's probably the best way to do it if you're also asked for intervals of increase and decrease. But in this case, we don't need to know those intervals of increase and decrease. We just need to know what happens at those points. So I'm going to use the second derivative test. If you have to show your work, you would find your second derivative and then sub those values in. Oftentimes we'll let you use your calculator for that second derivative, so just read the question carefully to see what you are expected to do. But either way, we are going to find the value of the second derivative at each of those critical points. So again, either find the second derivative, take those numbers and sub them directly into this formula, or if you're using the derivative function on your calculator, you are treating the first derivative as the function that you're putting in. When you calculate that out, you should get -6 for x equals 1, and you should get 6 for x equals 2. The important part here is the sign. This is a number that is less than 0. Right, so we have a concave down, and that means we're going to have, by the second derivative test, a maximum. This is a number that is greater than 0. Positive means concave up, and by the second derivative test, that means we have a minimum at that point. Now in this case, it does say find the max and mins, so we should be going back and finding the y coordinates. If we're asked to find max and min points, you want the x and y coordinates. So we have a minimum at 2, and if you put 2 back into the original function to find y, you're going to get 1 as your answer for y, and we're going to have a maximum at x equals 1, put that back into your function, and you should get a value of 2 for your y.